Thank you, and thank you very much to all of you, and congratulations for your fortitude tonight in being present, given the weather outside. It's a great honor to be at such an august establishment, but I have to say I'm less terrified than I was a few weeks ago when I had to give a talk about space to my grandson's class of 5- and 6-year-olds, who are a much more terrifying and difficult audience. But I hope you're going to be better behaved than they were. So today I'm going to talk about satellite observations and the importance of observations for climate. And this is something which I always pinch from Charlie Kennel, and a paper of Charlie Kennel's, which for me is a very nice example of why we should be talking about more than temperature when we talk about climate. You wouldn't expect to go to hospital, have a thermometer stuck in your mouth and be then diagnosed from that. You'd expect to have all sorts of observations made about you. And so it is with the Earth. And the body that's been put together to coordinate those observations is something called the Global Climate Observing System, GCOS. This is organized by different UN organizations, the WMO, the FAO, the UNESCO, UNEP, and the International Council of Scientific Unions. And they've come together with a body to ask that body for the last 25 years to coordinate the requirements for observations, to facilitate and to advocate for those observations to be made. And these have culminated recently in the publication at the Paris COP21 in 2015 of the current status of climate observations. And then we followed that up a year later, at the end of 2016, by a plan for what the future observations should be and how we should make them. And now we're in the process of trying to coordinate and make those observations worldwide. Now, in the past, GCOS has been mostly about what are the observations needed for modeling and prediction of climate. In other words, the understanding of climate and understanding where it might go in the future. For those familiar with the IPCC, it's essentially the work of Working Group 1 of IPCC. But more recently, it's become clear that the other aspects of climate, which is to do with the mitigation of emissions and the adaptation to climate change, to unavoidable climate change, and to understanding what the impacts are and how we deal with those impacts, are also very important. And so we're looking now not just at the work of the Working Group 1 of IPCC, but also the work on Working Groups 2 on adaptation and mitigation. And this comes out in the Paris Agreement. If we go back to the 14 articles of the famous Paris Agreement from December 2015, then everybody's heard about the 2 degrees or the 1.5 degrees of potential temperature rise. And you also heard something about emissions and the fact we need to restrict our emissions in the future to achieve that. But in fact, all 14 of those articles which set out the agreement that was made in Paris have something to do with observations. They all require information, data, and observations in order to be able to implement them. And it could be about loss and damage, which is very important for the small island states, for example, and those countries who have been most at risk from climate change, on adaptation, on early warning systems, and particularly for us on the Agreement Article 7, which is about strengthening scientific knowledge and research and systematic observations. So that's the core of GCOS's remit. But it spreads really across all the different articles which came out from Paris. And the core business of GCOS is providing information on the so-called essential climate variables, the ECVs. And these are the 54 ECVs which are currently established. We needn't go through them all, but simply give you an idea of the sorts of parameters which are needed in order to be able to drive climate models. So things like surface temperature, surface radiation budget, obvious sorts of things, soil carbon, the amount of carbon that's in the soil, below ground biomass, above ground biomass, soil moisture, hydrology, sea ice extent, and ocean parameters are very important. So there's a whole range of different observations which are needed in order to cover these 54 different parameters. Of those 54, about a half are directly observed by satellites alone. And of the remaining half, about 50% of that information comes from satellites too. So satellites provide about 70%, 75% of the information which is needed in order to understand climate. And that's why, coming from the space domain, which is where I've come from, satellites and their observations which they make are so important for climate. Now, we also talked about sustainability, and sustainability these days is really enshrined in the 17 Sustainable Development Goals which were agreed by the United Nations. And of these 17 which are set up there, 13 is specified specifically to do with climate. But it's quite clear if you look at the other 16, then very many of those, probably about a dozen or so, have very distinct and specific relevance to climate. Things like health and well-being, sustainable energy, water availability, and so on, are all aspects of climate, and where climate services have been need to be developed in order to be able to provide that sort of information to help to manage society and to manage the Earth as a habitat for mankind. So when we talk about climate, it isn't just something which we can talk about one day and then come back to the other problems of the world later. It really is something which, either fortunately or unfortunately, whichever way you look at it, underpins so many of the different problems and so many of the aspects of sustainability which we see from the SDGs. Now, looking again back at the implementation plan for GCOS that was published in 2016, there are a number of different aspects of it, and I'll try and cover one or two of those in detail. The first on climate indicators. Now, coming back to the cartoon of the Earth in bed, up until now you've heard, no doubt, a great deal about rising temperature, the 2-degree limit, the 1.5 degree limit, but also the historical temperature rise and the arguments that have been had about whether we do in fact have temperature rise or not. Do we have the hiatus? Do we have plateaus? And you can see that this is the history of temperature over the last 150 years or so. And if you look, it is a very erratic change. There is clearly strong evidence for an increase in the last 150 years. But it's not direct, and if one removes different bits of the data, then it's quite easy to argue that this isn't, it's not actually showing us the same sort of secular change that we expect from climate. And this has been the source of a lot of the arguments by deniers in particular, who say, well, if you take out this data, perhaps ignore the last few years, and it's all flattened out. You heard the arguments about the hiatus in the period between 2000 and 2010. If you imagine we didn't have the data for the last few years, which have been extremely hot, then there was an argument that things had flattened off in 2000 and global warming had stopped. Well, it's quite clear that isn't the case, but the data set is not necessarily the most robust that you would have if you wanted to have a single debate about climate. Then I wouldn't say that temperature has some advantages. It's important for us all. We have a nice long history. It's very precisely measured for the last 150 years or so, much more than any other parameter. But thermodynamically, it's not the best parameter, because very little of the energy which goes into warming the Earth as a result of the greenhouse effect goes into warming the surface atmosphere. And this tells you exactly where it goes. It's a very important diagram from the last IPCC report in 2013. And it shows the amount of energy which the Earth has absorbed, or how much the Earth has warmed up as a consequence of trapping more energy from the sun. And there are a number of things that one should firstly notice about this graph. It's for the last 50 years, roughly. Firstly, if you look at the last 30 years or so, then you have pretty well a monotonic increase. There's no hiatus. There's clear evidence that we have a strongly increasing and continuous change in the amount of energy which we're absorbing. You have little blips in 98, 99, and 1982, which are associated with the El Nino events at the time. But pretty well, it's a continuously increasing curve. So no hiatus, no arguments about that. Secondly, the error bars, shown by the dotted lines, are quite narrow and getting much smaller. So we're quite convinced, we're quite sure about that. Now look at where the energy is going. The pale blue is in the upper ocean, in other words, from about 700 meters to the surface of the ocean. The darker blue is between 2,000 and 700 meters in the ocean. We don't know much what happens below 2,000 meters, probably not a lot at the moment. But you can see that over 90% of the energy which we absorb from solar radiation goes into warming the oceans. And there's a few percent goes into warming the ice caps and sea ice, a few percent into warming the land, and about 2% into warming the atmosphere. So when we look at surface temperature in the atmosphere, we're actually arguing about this little maroon line down here. So we're looking at the last 2 centimeters of a dog's tail as it walks past and arguing about what sort of dog it is. Why don't we look at the whole dog? The other thing that we should note about this is just the magnitude of the change. Over the last 50 years, there's been an increase of about 250 zettajoules. Now, a zettajoule is 10 to the 21 joules, which doesn't mean very much to me either. But if we think about the total amount of energy which mankind generates from all forms of energy generation, fossil fuels, nuclear, renewable, transport, everything else, it's about half a zettajoule a year. So in other words, we're absorbing 10 times the amount of energy that mankind generates each year simply by improving the way that we trap energy from the sun. So there are a number of things to say about this graph, and it tells us a lot of information about the way the Earth is behaving and what's driving the climate system on the planet. The other thing that we can measure is CO2. Clearly, it's very important. CO2 and its equivalents in the atmosphere are what's driving the enhanced greenhouse effect. And if we look at the increase over the last 50 years again, 40 years there, again, you can see that we have an increase now to just over 400 parts per million from a traditional pre-industrial level of about 270 parts per million. So it's about a 50% increase over the non-anthropogenic sources. And that level has not been breached for the last million years or so, we know of. And in fact, last year was the highest, or 2015, was 2016, which is the last year for which we have full data calibrated, was the largest increase year on year, which is the bottom graph there, which is the growth year on year. Another important aspect of climate change is sea level rise, and you, I'm sure, will be familiar with the fact that we've had over the last 30 years sea level rising at about 3 millimeters a year, roughly, slightly accelerating at present. And what's very nice about this as an indicator of what's happening in the system is not only can we measure it, but we can actually understand something about where it's coming from. So there are two main components. One is thermal expansion of the oceans. As the oceans warm up, so they expand like everything else, and that gives us the green trace. We also have water runoff from glaciers, from land-based glaciers and from the ice sheets, and that's the red trace. If we add those two together, we get the red. Sorry, that's the blue. Add those two together, we get the red. But we can measure directly the change in sea level by altimetry, by looking at the topography of the ocean surface. So that gives us a measurement then directly of sea level rise. And fortunately, or rather nicely, our direct measurement of sea level rise agrees very well with the two elements, with the sum of the two elements we know as being the cause of sea level rise. So we have some idea that some confidence that we understand why sea level is changing the way it is. It's not changing uniformly everywhere as a result of ocean circulation, primarily in wind patterns. And you can see that, unfortunately, in some areas which are most susceptible and least resilient to sea level rise, we have some of the worst examples of some of the areas where sea level is rising most rapidly, particularly, for example, around this sort of area here in the Solomon Islands and in the Southwest Pacific, where you have a number of somewhat small island states which are extremely susceptible to sea level rise. But unfortunately, it's there that as a matter of the physics, that's where things are happening most. Sea ice extent, again, you will be very familiar with this, I'm sure. This shows the Arctic and Antarctic extension of sea ice, so floating sea ice, not ice sheets. And this shows you in the heavy purple curve the average over the last 30 years or so, plus or minus 2 standard deviations in the grayed area. And then you can see what's happened. The maximum, the pale blue is what's happened in the last year. So there is a range, but we're increasingly going further and further down in that range as time goes on. Another way of looking at that is looking at sea ice volume. And this is from a project called Biomass. And this shows the total sea ice volume in the Arctic. And this shows it's going back from 1979, around the clock, up to 2016, month by month. So the sea ice maximum occurs in March, April, May, and the minimum occurs in September. So you can see since 1979, the sea ice minimum at the end of September has come down from about 17,000 cubic kilometers down to about 5,000 cubic kilometers. And this is where you hear talk about the potential disappearance of sea ice in the Arctic by the middle of the century or thereabouts. So we have a number of different indicators now which tell us about the way that climate has changed and the effects that climate change has had, some of the different aspects on the Earth's surface. And I think this gives us a much better picture of the way that the Earth is changing as a consequence of changing climate than simply looking at temperature alone. So that's looking at historical change, but really, that's so what? I mean, that's told us about what's happened, but that's not all that useful to tell us about what's likely to happen in the future. And what will happen in the future will depend on how climate changes in the future, and that depends very largely on how we maintain our emissions. So mitigation of emissions is also an important aspect which is dealt with, and that's the primary aspect that's dealt with in terms of the politics in the Paris Agreement. And there are two aspects to mitigation. One is changing land use. So if you go from one type of land use to another, then there's a certain amount of emissions which can be calculated as per acre or per hectare of land use change. There's a certain emission coefficient and factor which is associated with that. The system for doing that in the UN is extremely crude. There are only 6 different types of land cover in the world which are considered. And so this has been going on now for the last 30 years or so, but the numbers there are relatively small, apart from deforestation, which is the main part of it. But the other part, which is now becoming much more important, is our discussion about controlling our emissions. And this is where we are beginning to have some observations now. We have some CO2 measurements that are made from tall towers and others which are very important on the ground. But for the first time in the last few years, we begin to get satellite measurements of CO2 in the atmosphere. Now, this is an extremely difficult problem, and just how difficult it is you'll see in the next slide. Now, this is a simulation or reconstruction of the CO2 concentration over Europe for a period of about 2 weeks in 2008. It is taken by combining the EDGAR database, which is the official database of national emissions, which is maintained by the Joint Research Centre in Isbra of the EC, combining that with a land cover model from a German institution which looks at the natural absorption and emissions of CO2 from natural phenomena, coupling that with the weather, and then tracing that across Europe. So if you were able to sit above Europe for 2 weeks in a rather speeded up version, and if you had eyes which are sensitive to CO2, this is what you would see in the atmosphere. Now, it's all jolly clever. The thing that's really depressing about it is that, of course, that's what we would like to know if we wanted to understand something about how we maintain and control emissions. But that's not what we observe. What we observe is an extremely small and poor subset of that, subsampled highly temporally and spatially, so that one has very distinct points well distributed in space and only very infrequently. So that's why we need to have many more observations about CO2, both from tall towers, from Mace Head, for example, out in the west of Devon, in west of Ireland, from Devon, which is where the UK gets the single measure from, and from a number of points around Europe. But also we need to have the sort of coverage in order to get the spatial distribution and patterns which you see there. You have to get that sort of information from an overview which you only get from satellites. So there are a number of different agencies now around the world, in the US, in Europe, in Japan and in China in particular, who are building and putting together a global system to work together to be able to provide better information about the time-varying changes of CO2 in the atmosphere. Eventually, to be able to not police the Paris Agreement, but to at least demonstrate that the declarations which are being made by countries in the UN as a consequence of the Paris Agreement are at least consistent with the observations which you make outside. If you were to give the UNFCCC the capacity to actually monitor accurately every country's emissions, they'd probably have a baby. They wouldn't know what to do with that. They would be terrified if they had the power to be able to go to a country and say, you've told us that your emissions last year were 73.2 million tons of CO2, and in fact, we know that it's 73.4 or 89.6 or 152. I really don't know what they would do with that information. But at least this way, we might be able to persuade countries that if they aren't reporting accurately, then there is a way of being able to understand whether the totality of those observations is consistent with what we see. So the EU is, I'm allowed to say that still, aren't I? The EU is taking a lead in this, and through the Copernicus program in the European Union, there will be launched in mid-2020s a new system which will help to support the global initiative for CO2. So the other aspect of climate we should mention is adaptation. And adaptation is very important because that's essentially about how do we adapt, how do we deal with the changes in climate which we can't do anything about. We'll try and do something about the ones we can mitigate if we can, but we're still stuck with the things that it's too late to mitigate, or we're not going to be able to mitigate in full. So adaptation is very important, and even Davos thinks this. If you look at the World Economic Forum in 2016, this was their This is their map of risks of severity and likelihood impact plotted against likelihood. So very bad things up on the top right, and up on the top right you find failure of climate change, adaptation, mitigation. 2016, 2017, extreme weather events, natural disasters, failure of climate change, mitigation and adaptation, 2018. So the WEF has discovered over the last 3 years that the most important threat to mankind, even above global financial collapse, terrorism, everything else, the highest risk and the highest likelihood of occurrence is associated to climate change. And why is that so? Why is that so important, and how does that happen? Well, this takes a little bit of explaining, but if you bear with me, in 2003 we had a heat wave in the south of France and northern Italy, killed about 60,000 people over and above the normal death rate for that year. And there was an average of 2.3 degrees Celsius above, 2.3 degrees anomaly, 2.3 degrees above the normal values for that year. And that translated to about 50 or 60,000 deaths. Now, what you see here is a predicted anomaly. This is some excellent work done by the UK Met Office, in particular Peter Stott and colleagues there who are doing really a tremendous job in this worldwide. And what you see here is in the blue Gaussian curve is the distribution of anomalies if you didn't have any anthropogenic climate change. This is what you'd expect to see. And the red is when you add anthropogenic climate change in. This is the distribution of temperatures you'd expect to see. So what you can see here is there's a relatively small shift, about a degree or so. But if you imagine what's the likelihood of an event occurring here, say. This is a one standard deviation heat wave of 1.6 degrees. You can see the likelihood of this occurring, which is essentially the intercept on this blue bell curve, is hundreds of times smaller than the intercept on the red. In other words, you've only had a change of about a degree in 100 years during this period of climate change. But the likelihood of such an event occurring has gone up. This is the quickest way of looking at it. So from 1900, it was about a 1 in 100 year event. Even by 1990, it was still only a 1 in 50 year event. But now it's a 1 in 5 year event by 2010. And if we get to 2025, it'll be 1 in 2 on current trends. And by 2040, that sort of average temperature in summer would actually be cool. So what we're seeing is that the small changes in apparent temperature, which, so what's 0.8 degrees? I mean, so what? Nobody even notices that. The point is that the extremes which occur as a consequence of the change in that anomaly are extremely large, and you have many orders of magnitude greater risk of events occurring. It's highly nonlinear, and some excellent work has been done by David King of this parish in looking at similar aspects, where if one tracks the response of populations to temperature change, then nothing happens for a few degrees, and then suddenly you go through essentially like a phase change in the population. It's like a mathematically catastrophic change, where suddenly you go from nobody dying to everyone dying. And this happens at quite an explicit point. It's not something which occurs gradually over a long period. So we have to guard against these sorts of events. I mean, many other things will happen as a consequence of climate change as well. And one economic aspect is, just as an example, is the change in per capita output. You can see that, unfortunately, when this is modeled, I think this is from an OECD paper, you see that it's countries which are least able to really manage climate change are the ones which will be most economically hard hit, in the tropics in particular. So coming back to our sustainable development and how do space agencies support the SDGs. Just to give some examples, as I said, one could go through all 17 of them and spend the rest of tonight and several more giving examples there. But I'll just try and show you a couple of examples from amongst those where we have looking at food security. How do we use satellite data to help improve our understanding of food security? This is a study that was done in the Ukraine using complete coverage, using high-resolution satellite data. And from that, we can deduce the different crop types and the yields from those crops and map the likely outcome in terms of the crop statistics by administrative area in Ukraine for the growing season of 2016. And you can do this for anywhere, just taking one example from Ukraine. So we can get very good information directly from satellites using just the reflectance information we get from the crops to give a yield prediction and how that changes as a consequence of climate change. Water is also very important. Water, amounts of water, quality of water, distribution of water is clearly absolutely necessary for healthy mankind. And satellite data are also extremely powerful in being able to look at that. If we take this example from an area in Gabon, this is some work that was done with the Ramsar Wetlands Convention. Ramsar is not an acronym, it's a place in Iran, in fact, which is where the convention was signed. And this is the body which monitors the distribution and health of wetlands worldwide. And this shows just both the power of satellites in able to monitor those in very small areas, but also the improvements in the last few years. So what you see on the left there is the mapping which was done by Landsat, which I'm sure you're all very familiar with. And this is now what you see today with the Copernicus Sentinel-2 mission. And if I toggle between those, you can see the improvement in the resolution and precision of the measurements which can be made. So we are getting much better understanding now of the distribution and lifetimes of standing water bodies. Perhaps a bit more controversial, and I won't claim this, I'll simply say this is an example that has been claimed. There are also counter-arguments. We know from measurements made by GRACE, which measures the amount of water, the mass of water in aquifers, basically, to put it simply, that in Syria, in about 2008, there was a significant and rapid decrease in the amount of water in the aquifer. This was a result of the local drought, and you see this in the previous slide there. So where the water decrease occurred mostly in the areas of red. And this was subsequently followed by a significant movement of the mass migration of people from the areas, the agricultural areas, into the cities, and cities became increasingly unstable with the result that you see today. Now, I would never, by any stretch of the imagination, say that what is happening in Syria today is a consequence of a particular climatic event in the northwest part of Iran, southern Turkey, and in Syria. However, one can certainly believe that there are complications and implications there from that change which are of significance in the social problems which we see there today. So this is the sort of thing, this is where we had enough problems in Europe with 1.5 million migrants coming from this area. Imagine this happening in sub-Saharan Africa, where you have maybe 100 million economic migrants who might be generated as a consequence of this in areas where you have the most unstable countries on the planet, which line up side by side across the area just below the Sahara. Now, I'm not doom-mongering. I'm not saying that there's going to be millions of people suddenly evacuating Africa as a result of this. However, we know that sub-Saharan Africa and the area just below in the Sahel and just below the Sahara itself will be extremely susceptible and vulnerable to climate change, to food security. And we know that the people there will likely have a very difficult time as a consequence. And this may well be one of the consequences of it. So as I say, I'm not being a doom-monger and saying this is what will happen, but one doesn't have to be very imaginative to understand that there may be consequences which may not be what we would like to see even in Europe if we take a rather parochial perspective. Cities also important, and there's an increasing trend for populations to move towards cities, as I'm sure you're aware. Cities are also very effective in dealing with policies like this and dealing with climate change, amongst the most important polities worldwide. I think it's because they have relatively well-defined problems, usually one problem for a given city. It's flooding, or it's drought, or it's coastal erosion, or it's ingress of water by sea level rise, or some other particular problem. So they have a focused problem. They have a focused geographical area. They generally have a fairly focused political entity in respect of it, and they generally have budgets as well. So in terms of dealing with adaptation to climate change, some of the most impressive programs worldwide are those which you see in cities. And they can be helped by looking at, for example, detailed informal settlements, detailed mapping of informal settlements on the outskirts of cities. We also see from satellites the changes in air quality. And this is the Po Valley. Anyone who's ever tried to land in northern Italy between about November and March knows that trying to land anywhere in the Po Valley is a waste of time. What you see here, though, is air quality in PM 2.5 micron particles. And the difference between a typical Sunday, when people are sitting at home having long lunches, and a typical Tuesday when they're all traveling to work. And this is the difference in the air quality you see along the Po Valley, which runs from up here across to the Adriatic. This is the delta here of the Po. And you can see this is an area which is very much trapped between the Alps to the north and the Apennines to the south. So you have a basin across here, which is where the Po runs. And you can see the changes in air quality as a consequence of different use by people during different days of the week. And lastly, if we talk about general sustainability, then one of the most important of the SDGs, and one where satellite data are particularly useful, is looking at land cover. Many, many different aspects of sustainability have something to do with understanding of land cover and land cover change, land use change. One of which is, for example, here, the distribution of forest and wetlands and different cover types. And being able to monitor those at high resolution, the resolution of 10 meters or so, frequently, better than once a year, and to be able to provide global maps at that resolution, or maps anywhere in the world, I shouldn't say. It's not global. We don't want necessarily a global map, but we want a map that we can find anywhere on the planet to be able to look at the way that ecosystems change, and we can do that now quite easily from space. And we've been doing that for some time, producing global maps at 300 meter resolution, and now increasingly at 100 meter resolution every 5 years or so, working with people like the Food and Agricultural Organization of the UN, UNFCCC, the Convention on Biodiversity, the UN Convention to Combat Desertification, UNCCD, and the UNFWCMC, the World Conservation Monitoring Center, which is up the road here in Madingley. So again, this is the 15th of the SDGs, which is extremely, it's helped enormously by having better information from space. Climate change impacts, we could spend all night on this, but just one example of the power of satellite data to be able to understand what that might be. If we look at sea level rise in the Netherlands, then what we've been able to do is to take several satellite images, and by comparing the phase of these radar images over a period of time, we're able to see the changes in subsidence of the dikes as a function of time, down to about plus or minus a millimeter a year, mapped in color code as you see there. So the greatest subsidence is in the northeast corner, and drops in the middle, and then a little increase in the southwest corner. What this has done, together with the predictions of sea level rise, is for the Rijkswaterstaat in the Netherlands to increase their expenditure on dikes from about 50 billion as to what they were planning to about 80 billion euros because of the changes, the acceleration of sea level rise which they detected, together with information about the structure of the dikes. And just as a comment, you can actually see this happening in London as well, where they built the Jubilee line and the National Grid cable tunnel. You can see the subsidence that was caused by those as well. So those are different examples of where we can understand climate change as a result of the observations we make. We can do something to help mitigate change in the future. And today, we can do something to try and help adapt to the unavoidable climate change which we already have. And these observations can help in all different aspects of that part of the problem. So thank you very much for your time.
Earth observation has now in ways that were probably completely unimaginable even just a few years ago, in terms of the sort of information that we're now able to achieve by looking at the Earth from space. So,
right.
Thank you. Please, if you sit down now, we've got time for extended question and answers. So if you're watching online, please send your questions in. There's a Twitter hashtag somewhere around here. Questions in. We'll start off though with taking some questions from the audience. So who wants to ask first?
Hi, Thanks, Steve. Can I ask about the accuracy? So some of the things you're talking about are underground, and you're talking about sort of agricultural yields and so on. How accurate are the data in terms of estimating agricultural yield or soil carbon, things that you can't obviously see from anywhere, let alone from a satellite?
No, as I said, of the ECVs, 50% come from satellites directly. Soil carbon is one that doesn't, not surprisingly. That comes from elsewhere, but the information on that is very poor indeed. In terms of agricultural yields, then what one can map very precisely from space and very easily is the extent of different crop types. And with some understanding of the yield patterns, one can look at the vegetation vitality during the course of the growing season. And from that, and from knowledge of the hydrometeorological data which you have for the area, then one can get quite good estimates of yield per acre or per hectare, and then you can multiply that up by your aerial coverage. That's an interesting question, which is one of the unintended consequences of changes in policy, for example. And at one time, the CAP in Europe was paid, payments were made as a function of extent. So if you had 150 acres of barley, 150 acres of winter wheat or something, you got paid a certain amount for it. And that led to an enormous boon in the use of satellite data for monitoring the extent of different types of land cover and crop. And then the Commission decided they would do that on the basis of yield as opposed to aerial extent. And the bottom fell out of that market immediately because it was much more difficult to understand from satellite data, particularly at the time where the data were much less complete. So it's interesting how a change in the policy, which was completely unintended, had a significant effect on that particular part of the industry.
I mean, maybe I can ask a question that follows on from that. It struck me very much as you were going through your presentation was that there are increasingly large number of satellite observations that clearly could feed into a policy agenda. I mean, you know, even just your emissions of particulates and literally changing, you know, between different days of the week, clearly might feed into a particular policy. Do you get the sense that policymakers are keeping up with the advances in conservation capabilities, or is there?
I don't think they are, and I don't think it's their fault. I'll try to be brief because it's a bit of a hobby horse, but 15 years ago we tried to set up something in Copernicus, which was a program of environmental information for Europe. It's a very good idea 20 years ago. And the first concrete steps were when ESA set up some services in 2002, 2003. And we admitted that we didn't know what the right services were, what were the key areas of policy. So we said, fine, we'll fund up to 10 services, and we'll invite people to make bids for those services, but they had to come along with their partners. They had to come along with the people who said, this is my problem, and this is how I'm going to use the satellite data. I think they were reasonably successful. I mean, they didn't solve all the problems, but they were a reasonable model. We then moved on to a much more powerful phase of the Copernicus program, which is now a sort of 10 or 12 billion program. And inevitably what's tended to happen, it's a tremendous program, so I'm not complaining about it, I'm not knocking it. It's a fantastic achievement, and the world is envious of what Europe has done in that. But inevitably we tend to do the things we know we can do, rather than the things we find difficult. So the first thing we did with the Copernicus program was to build more satellites, because we know how to do that. In fact, we had quite a lot of satellites already. We didn't have enough, and they weren't. The key thing about Copernicus data, the Sentinels, are that they are continuous and they're guaranteed for 30 or 40 years into the future. So you can actually create a business model which relies on accessibility of satellite data, which you couldn't before. But nevertheless, you know, we sort of slipped away from this critical area in the middle, which was how do we provide the right information to, oh, not sure about that, but we could build more satellites. So we built more satellites, and they said, well, now we need some services. So the Commission's put his hand up, and there's now funding 600 million or something of services. And the service is actually not, and this is no criticism, and the people who run them would agree with me completely, that they are not so much services, they're wholesale services which collect information and store it and make it accessible. The trouble is, it's the analogy I've used before, it's like having a warehouse full of shoes when you want to buy a pair of shoes. So you've got the factory that builds the shoes, you've got the warehouse with 6 million pairs of shoes in, and there's you standing outside wanting to try and buy a pair of shoes, and you don't know where to start. What we're lacking at the moment is somebody setting up a shop and saying, well, I'm going to cater for the 25 to 35-year-old market for summer shoes, goes into the warehouse, picks up 500 pairs of sandals or something, comes out, puts them in the shop window, and you can go along and buy one. And that's the bit that's missing. It's this sort of retail end of climate services. And the reason they're missing is they're very hard to build. It's very hard to understand how you do that. It's really difficult to really understand what the policy problems are that you need to address, which are the most important ones. And very hard to understand how you can actually convert the information, the data you have, into the right sorts of information. And it's not just about satellite information, it's not even about physical information. It's about demographic, social, economic information, which are not as nicely packaged. They come in all sorts of different shapes and sizes. And putting all these together to try and serve some policy is really quite difficult. Science is very good at saying temperature will rise, sea level will go up by this much, plus or minus a bit. It's very bad at asking the inverse sorts of questions, that given temperature will rise, sea level will go up, CO2 is going to go up, will my house flood? It's not very good at answering that sort of question. And those inverse problems are the ones that we really need, are the difficult ones, and the ones that society needs to be able to ask and get answers to. We've got one over here at the moment, and then you get the microphone.
Yeah, my question is about policy as well. With all this wonderful observational data, if you had a hotline to the Environment Secretary of the UK, what would you want him or her to enshrine in law to actually get something into action?
That's a fairly frightening thought to begin with, hotline to Michael Gove. Probably something to do with badgers, probably, but that's a very good question, and really one that's hard to nail. I think I would back out of it a little bit by not giving a specific answer, but to try and, first of all, we live in a world of policy-based evidence. People decide what policy they want, and they go scrubbing around looking for the evidence which supports it. And if they can't find any, they manufacture some. It would be nice if we lived in a world of evidence-based policy, where people actually said, we have a problem to do with X, Y, or Z. Let's understand all we know about X, Y, or Z, and then decide what we should do about it. Unfortunately, with our current politicians, we tend to go the opposite direction, which is we have a fixation that we want to do something or other, and we scrabble around to find some reasons to why we should do that. So that's probably what I'd say to Mr. Gove if I did have a hotline. Think about what it is you want to do and then decide on the evidence rather than the other way around.
How much has the years, and which new technologies have had the most revealing impacts?
I'm always tempted to say the next ones. We're always on the brink of a breakthrough, but there have been some very substantial changes in the last few years with new types of measurements. Over the last, say, 20 years, things like altimeters, which tell us about the ocean surface and tell us about ocean circulation, distribution of ice, sea ice, and so on, has been incredibly important, particularly with ice thickness, which we are now able to measure for the last 10 years or so, 8 years, with cryosat, which we weren't really able to measure before. We could measure ice extent by looking at passive microwave imaging, which told us where the ice was, but didn't tell us anything about how thick it was. Now we know that, we can say something much more about the way the ice behaves and how it behaves year on year. So that's one classical area. Atmospheric chemistry, and we're in the middle, or I hope just at the beginning of an explosion of information about atmospheric chemistry. Beginning to see the first of those, particularly for CO2, methane, and other gases, and also particulates. Interferometry, the technique of being able to use the phase information from radar systems, not necessarily for climate, but that's been a way of being able to get much more information about tectonics, about geophysical behavior of volcanoes, earthquakes, and so on. Unfortunately, usually demonstrates mankind's stupidity as well. We're busily building Port-au-Prince in Haiti on the place where the next earthquake is going to occur. And the same thing is true in northern Turkey as well. We don't know when it's going to occur, but we can tell you exactly where it will be, because one knows exactly where the slip fault is, and you can see the slip of that using interferometric techniques now. And so they just moved a little bit along the fault from the place it slipped last time to the place where it's about to slip next. So that aside, that has lots of implications. I showed an example with the dikes, but also with subsidence caused by different types of excavation. And that actually has been used to sustain certain legal activities as well, and predicting subsidence in areas where we haven't seen that before. So that's another new technique. We have something else which will be launched later this year, we hope, after many years of delay, which will measure, it's an atmospheric LiDAR. So it beams down a laser system into the atmosphere, it's scattered back by the particles, and by looking at the Doppler shift in the return signal, one can measure the velocity of those particles moving, which tells you then, you can then reconstruct a three-dimensional wind field in clear air, which has never been done before. At the moment, we measure winds by a rather simple technique of taking a picture of clouds, taking another picture of the clouds a few hours later and seeing how much they've moved. They're called atmospheric motion vectors, which makes them sound very, very sophisticated, but it's what a child of 5 would do with 2 tracings. That's obviously only works when we have clouds, but where we have no clouds, then at the moment we have no way of measuring wind in the atmosphere, and that's something of a holy grail. So we have made some achievements. Soil, there's another mission which has been launched by ESA, there's a similar one in the US, called SMOS, which measures soil moisture and ocean salinity. And those are 2 critical parameters as well. Soil moisture is extremely important for all sorts of reasons in terms of controlling exchange of energy, momentum, heat between the atmosphere and the land surface, but also very important for practical reasons of agriculture. And we have very, very poor understanding of soil moisture generally. I mean, most of our measurements, if you go to the European Centre for Medium Range Weather Forecast in Reading, they will have a map of soil moisture on the wall, which will tell you this is their best estimate today of the world's distribution of soil moisture. But most of the data which have gone into that are 6 months old and completely wrong. And they know that, but it's the best estimate they have at present. So improving the quantity of soil moisture. And that's a very, very difficult measurement because you're measuring the dielectric properties of the top 2 centimeters or so of the soil, which is also affected by all sorts of other things, nothing to do with soil moisture. And it's even more difficult to do that in salinity in the ocean, and salinity is very important also for give a better understanding of ocean circulation. But we've made some starts on those measurements, which are very important. So we're improving the old measurements of the simple things that we could do, like imaging. We're doing much more frequently at higher precision, better radiometric precision, more channels, more frequently at higher resolution, and so on. But there are new types of techniques which are being developed, which will be very important. One which everybody would like to see is something which will look at active CO2 in the atmosphere. So to have a CO2 LiDAR, which would be able to beam down through from space and look at the signal back and tell us very precisely how much CO2 there is in that column. At the moment, the measurements you saw there, the different systems which are being developed, are measuring passive CO2. So it simply looks at solar radiation and essentially looks at the spectrum coming through, and from that detects the amount of CO2. But that leads to very high errors, part per million, which doesn't sound like very much, but it's big by comparison with neat measurements you need. If we could do that using active information, basically you're shining, instead of relying on sunlight, you're shining a LiDAR down at the right frequency, which is enormously more powerful than the sunlight. And we look then at the return signal, we get much better understanding of the location and also the precision of the CO2 or other gases measurement. But LiDAR technology is a really, really difficult technology that everyone the world over is trying to improve.
I'm going to ask you a question that's come in online.
Not from Mrs. Trellis. Not from Mrs. Trellis.
In countries with large wetlands and other large sources of natural emissions, are satellite observations helping to attribute blame for emissions when establishing greenhouse gas emissions inventories for these countries? I mean, that alludes to one of the things that you were discussing in your talk.
I think even if we were able to measure precisely the amount of CO2 or methane emissions, and methane is probably easier to do than CO2, very directly, then I'm not sure how the political world would actually deal with that information. Would you expect there to be some sort of international police system which would go in and tell a country that it shouldn't be doing this or should be doing that? I think we see enough problems with doing that in other spheres. What we would really like to have is a way of being able to provide sufficient information per country to establish whether the statements which are being made, will be made as a consequence of their agreements in Paris in 2015, are consistent with the external observations. I think we wouldn't like to say that you're lying, but we would like to be able to say it's curious that the measurements that we make are not consistent with the statements which you're making. And I think that there is some power of persuasion which can be applied in those ways, but I don't think being able to go along with a big stick and saying you're telling lies will actually get anybody very far.
Second question online, which comes from Clara from Minnesota. Ask around tipping points, and in particular she's asking about methane and potential of methane release in the Arctic, and whether that's something that you can gain any insight on from satellite observations.
Yes, there were some crude measurements made by ENVISAT between 2002 and 2012 of global distributions of methane at low resolution, both spatially and temporally. So we weren't getting very precise information, but certainly one can detect the seasonal changes. It's a big issue at the moment in the States. In fact, I know I've worked with, there's an NGO in the States which is actually building its own satellites at the moment to detect methane. They've got a couple of 100 million sorted away from their donors to build a suite of satellites because they don't believe the emissions which are coming from some of the big fracking areas in the States at present. So there's a lot of political discussion about how better measurements of methane could improve that understanding. And I think, so the passive measurements have been made for some time and they're improving. There is also a French-led, but with the UK supporting system called Merlin, which is being developed for looking at methane emissions, which will be online in a few years' time. It's an experimental system, it's not global coverage, it's a very narrow swath, so it gives us experimental evidence. But we will be, there are many of these things which I'm quite optimistic about, and I confess to that. But I think generally speaking, when we look at the likely improvements in technology, we've generally been underestimating the capacity in the past compared with what actually has been possible. And so I think we should start being a little bit more optimistic about what we might be able to develop. But yes, methane is certainly easier to measure in the atmosphere than CO2, and I think that we'll probably be having quite operational systems to do that within the next 5 to 10 years.
And it's worth pointing out that methane emissions are happening. There's a particularly pressing need to try and understand methane emissions
Because of permafrost.
Was essentially flattening off.
Yes.
In the late period of the last century and early period of this century, and then we've seen a dramatic uptick taking the last 5 to 10 years or so. The cause of which is not yet completely pinned down, and it's important because it's a much more powerful greenhouse gas.
It's a more powerful greenhouse gas. The lifetime, so the issue of the lifetime is also very important. And there is an as yet rather poorly known likely response of the taiga and high northern wetlands to permafrost being released with warming of the soil. Then how much methane might come out from that could be a lot, and it's not clear at the moment how much that's likely to be.
Yeah, thank you. That was fascinating. Could you elaborate a little bit on international and global cooperation in terms of data access, and what are some of the challenges of the cooperation from the science side?
Generally speaking, that's one of the things that works reasonably well. After much deliberation, the Copernicus was a program set up by the European Union over the last 20 years or so to provide better information on the environment for Europe and its citizens, to quote. And there was a long debate about whether the data which would be made available from the Sentinel satellites and other forms of data from Copernicus should be freely available, both free in terms of zero cost and free in terms of open access. And I'm pleased to say that after many years of deliberation, that was achieved. So by the time the first satellites were launched, then all those data which you get from satellites are available freely. It's actually quite easily accessible as well. I've tried to do it myself. You can log on as Joe Blogs, and you can access and you can download as much or as little as you want. Somebody asked me the other day about I was at a meeting with an oceanographer in Geneva, and she asked me whether we had any information about the ship that was on fire in the South China Sea, if you remember, a little while ago. And just sitting in the meeting, I was able to log on, create a new account, try and download the images from the South China Sea to see whether I could find anything which actually covered that area in the relevant time. It was quite easy even for me to do, and I'm not expert at it. So we do have access to those data. The other data, the non-satellite data, are much less easily accessible, and some of those are becoming less accessible in time, particularly things like hydrology and the hydrology between different countries. Water is a significant issue between countries, particularly countries which lie along a single river, like the Danube, for example, or the Nile, as you're about to see with Ethiopia, Sudan, building a very large dam above the cataracts, which will have a significant effect on the annual floods of the Nile. So countries are very cagey about their hydrological data. Other forms of data, I think they're less well organized in terms of the access. But certainly, in principle, these data are accessible. In practice, it's more difficult to get hold of them than from satellite data. And certainly the US has had, for a very long time, a very open policy of access to all data. The same is true in Europe. In Japan, that's also the case. In India, in principle, it's the case, although in practice, it's quite hard to get the data sometimes. In China, in principle, it's the case, but the trouble in China is that several different agencies are responsible for different suites of satellite systems. And they have, in theory, all open policies, but some are more open than others.
But coming back to the point that you made just a minute ago about a shoe warehouse versus a shoe shop.
Yep.
The first lecture that we had in this lecture series was obviously Prof, who was discussing about climate change impacts in Bangladesh and the need to have information to inform adaptation strategies. And clearly, a lot of the information coming from Earth observation, in principle, ought to be very good at informing those sort of decisions. But, in a way, there's an extra stage that needs to be gone through in order to, exactly the point you were making a minute ago, to make that, it's not just simply making the raw data available internationally, it's actually making the downstream products that can actually be used in decision making.
Absolutely, and it's where we're all falling down, really. And I'm doing what I can to try. Even you take the WMO, I don't want to pin this on them, but just as an example, they created a tremendous World Climate Conference 3, WCC3 in 2009, I think it was, 2,000 delegates, prime ministers, heads of state, God knows what, all to set up something called the Global Framework for Climate Services. They were going to be the body which was going to deliver these sorts of climate services. And we're nearly 10 years on from that, nothing has happened. And I'm not blaming them for that. It's simply much, much more difficult than anybody realizes to do that. And I think the failing in the system, and it's not just the WMO, but a number of different people have tried to go ahead with this, and they've tended to wind up doing what I said earlier, which is you start off with a system, I'm going to build a system. So they sit down with a piece of paper and a pencil, and they design a system which looks like a wiring diagram for how something's going to work. And they build a data network. Well, you're lucky if they build it. They sometimes spend 10 years designing it. Occasionally, they might even build it. But it never actually delivers any data to anybody because nobody figured out what they wanted to do with the data before they started. So what we need to get away from is data systems being designed by data engineers and data systems being designed by people who have problems. So I'm a great believer, and this is why we did this 15 years ago in ESA, and I think it was successful at the time. We said, okay, there's 1,000,001 problems out there. We can't solve them all. We're not going to build a system to solve them all at once. Let's pick 6, and let's try and solve those. So we picked 6 or 7 different problems, which would do with food security, coastal defense, disaster risk resilience for specific types of risks, marine security, and a couple of others. I can't remember them all now. Deforestation as well. And put together end-to-end systems which included data providers, entrepreneurs, all sorts of systems through to, we had over 400 user agencies involved in these 10 services, and they ranged from local councils up to UN organizations. One of them was to do with air quality, and that actually started off with satellite information providing, like you saw there, for the Po Valley, and wound up with a service which was developed by a company in Cambridge, actually, which allowed people to have a tweet to their phone if they were susceptible, if they were asthmatic or something, to be told, today's a bad day in your area, don't go out unless you really have to. And that, I think, was an example, and that there was a lot of fuss about when I think it was Ken Livingstone was mayor at the time. This was published in London when he was mayor with something at County Hall. I know it was Boris, that's right. It was difficult to confuse the two, but yes, it was Boris. I think that was a good example of where you wind up with a really practical, and you started off with satellite data on a global scale of air quality, and you wind up with somebody getting a service on their phone. And I think you need to really learn by doing. You need to do one of these things. Then you need to do another one and another one. And you discover that actually some of the infrastructure you need for them all is common. And so you start building that infrastructure. But there have been very many unsuccessful and large, expensive projects which have gone the other way and said, well, if I need to do all these 55 different things, I can only have one infrastructure, so I'm going to design the infrastructure. And they build an infrastructure, they get to the end of the project, and nobody ever uses it because it wasn't the right one. So I think one needs to learn by doing, and building up these cases about how to actually deliver a real service to real customers, whether they be public sector, private sector, school children, whoever it may be, they're all customers for the information.
Thank you for the talk. I wanted to ask something. So this isn't my field, but I find it very interesting, and I can see a lot of potential benefits from it. I'm wondering, and I'll try not to, I don't want to be prescriptive about it, but I'm wondering what potential risks there are with having such granular data, whether that's that could be national or at an individual level. Could you maybe talk about that for a little bit?
You mean in terms of privacy or intrusion?
I'm trying not to be prescriptive. You mentioned examples of countries getting cagey about having that level of information available potentially at a geopolitical level. It could also be an individual privacy thing. I'm trying not to be prescriptive about it.
Yeah, well, I mean, here's something which there's something under the UN called the Open Skies Act, which states that international access to data will be free down to a minimum resolution of, I think, 0.5 meter is the current limit. So there is an internationally agreed framework which says that nobody can be possessive or prescriptive about use of data over their territory down to a certain resolution limit. So even if people are sensitive about it, then I'm afraid they just have to swallow that. Below that level, yes, then they can say something about it. And that's been agreed at all levels by all people. I think what the history is littered, this is just a subjective view, but history is littered with examples of where people have tried to achieve benefit by preventing access to information. And there are very few examples where it actually worked. And open access to data generally is a good thing for all concerned, even those who think in the first instance it might not actually be that way. Generally speaking, it turns out to be the best for all.
A couple of more online questions and then one question from the audience. So these are two questions which are actually quite interrelated, so I'll ask them at the same time. The first one is, which do you think are the easiest to cause climate variables to communicate to policymakers or indeed businesses or others to encourage climate action? And the flip side of that, which is the second question, is which climate variables do you think have already produced the greatest shift in policy or might appear to be the most useful?
Well, I guess the answer to the first question is really up to everybody can make their own mind up. The 7 or so which we put up there today were the consensus of a group of us who were involved in trying to figure out which would be the best basket of indicators for reasons of transparency, simplicity, global applicability, reliability, and so on. And those were the numbers we came up with. You may not agree with us, and you may well have your own favorites, all of you amongst those. I think my favorite is probably the one that's got nothing to do with satellites, which is ocean heat content. That seems to me the one which tells you more about what's going on in the Earth system than the others. But it's a bit less accessible and needs more explaining than some of the others. Temperature, for all its faults, and it has many, nevertheless is now ingrained in most people's ideas as being, we talk about climate change as being synonymous with global warming, which is not the case. I mean, there are many different aspects of climate change. But I think we have not entirely cracked the problem of deniers. There's some obvious ones around in the world. But we are a long way down that path, I think. So temperature, for all the fact that I have to grit my teeth and I say it, has probably been the most useful up until today. We are now seeing, I think there's a very wide awareness of things like sea ice extent, which is quite easily demonstrated, reliably measured, and I think there's a wider awareness of that. But I think everybody's awareness by definition is their own. It's what they see as being the most important thing.
And of course it depends on what question you're trying to answer. So these the variables that we're discussing, ocean heat content, for example, are very good measures of the question that you're wanting to address is the climate change.
Yes.
That, due to the greenhouse effect, increased amount of heat in the Earth system. But if you're wanting to understand what's happening in data, and to try and make, again, the sort of adaptation decisions that we were discussing a minute ago, then global ocean heat content is not necessarily the best measure to have.
No, I think the descriptors of climate change really are change today. Up until now, they are historical change, which is very important to understand what's happened in the past. But for the future, they're not helpful. For the future, you want to know is how is that going to affect me? What's going to be the major effect? Will my house flood? Will I have food security in the future? Will I be able to feed my people if you're a leader of a country? And those are the sorts of, they're the different types of questions. They're the what-if questions, the questions where you need to have a lot of more information than the simple historical, physical information about the Earth that we've had to date. So I think there's a fundamental change in, at the moment today, and it's always at today, whether it's today or tomorrow or the day after. History is important, but the future is more important, and that requires different sorts of questions and different sorts of information. And they're much more difficult to answer, even to pose those questions, than in historical ones.
I would actually need the microphone so that people online can hear.
Stephen, early on in your talk, you mentioned that you thought the people needed to have a broader understanding of the changing climate that went beyond temperature. And so you came up with a number of indicators that might enrich people's understanding of the climate. The question is, it won't mean anything unless people use these indicators. And there's a very important group that needs, I hope, that one would hope would use them, and that is in several years from now, the parties will get together, take stock of where they are, and try to decide whether they should increase their ambition for further emissions reduction. You've already addressed how satellites and so on will help on the taking stock by indicating, giving a general impression of how their commitments are faring in the real world. But the other part of it is, in order to make the decision to increase their ambition, they have to have a sense of how the climate is changing and how it affects them. So the question is, are there any arrangements that will provide a set of indicators to the people who will be negotiating increases in ambition?
And this is all in reference, the they here is the signatories of the Paris Agreement,
Right.
the countries that are signatories of the Paris Agreement.
That's a bit of you know perfectly well that's a very difficult question because you've tried to answer it yourself. There are two answers to that. One is that one could look at the things like changing temperature and so on, and one would hope to see in due course, and the problem is it's in due course, some change in the trajectory of those changes as a consequence of reduced emissions, for example. And one would expect to see that, but perhaps not for 10 or 15 years. And it's all counterfactual. That's the point. It's all, okay, what's the comparison with what's happened compared with what might have happened had we not done this or that? Now, you and I have worked recently on asking the sort of questions that you'd expect an intelligent politician to ask, which may be a tautology in its own right, or an oxymoron, I should say. At COP21, 2015, politicians made a decision to implicitly to suffer certain economic consequences of the decision which they took. They would suffer from reduced growth or something or other in terms of their economies in order to improve the likely trajectory of the climate for the world. So they took a conscious decision that they were going to do something that would harm their country. Probably. Certainly in the developed countries' case, the so-called Annex I countries. If you were an intelligent politician, you'd like to know whether that decision actually had any effect. And what was the benefit? So you know what this benefit is. You've said, I'm going to emit this much less CO2 in my country, and that's going to cost me a certain amount. The benefit of that to my country will be what? And how am I going to measure that? And the answer is it's quite difficult, as you perfectly well know, because it's essentially about its avoided disbenefits. So it's like the example of the heat wave I gave in the south of France, where something like 60,000 people, excess deaths occurred during that summer as a consequence of that one event. Now, if you allowed climate change to continue unabated, then you would have much more frequent events like that. You would have 60,000 or maybe 100,000 people dying, not once every 15 years, but maybe 100,000 every 2 years or something. So you could soon tot up the number of the consequences of that, of those particular actions. Supposing then you say, well, actually I did do something, and as a result we've gone back to having one of such event every 20 years instead of every 2 years. So we've had, in the last 20 years, 400,000 avoided deaths, and you can do the same thing in terms of infrastructure. So you've maybe had 200 billion less of destroyed infrastructure. It's all counterfactual, though. It's very hard in discussing climate change. There's no good news. And the only good news comes in avoided bad news. And that's why politicians are never very keen talking about climate, because talking about bad news is not what politicians do for a living. The other problem is that it's also very long term, and that's by definition politicians don't do that either. So I think all we can hope for is to be able to provide convincing counterfactual evidence that the effects of the decisions taken in Paris were such as to avoid future disbenefits to a certain level and quantify both the human cost and the financial cost of those insured or uninsured losses which would have ensued had we not taken those decisions in 2015. And that's a difficult argument to press.
But of course, the other side of what you just your opening statement there, that the country took, or Annex I country, developed country, took a decision that was going to cost their economies. I mean, even that requires counterfaction as well.
Yes. They sort of assume it's going to cost their economies, but I'm sure that they don't actually have much idea how much it's going to cost their economies. So when you measure cost benefits and you're not sure about the cost and you've got no idea about the benefits, it's quite difficult to make a...
I was thinking about the map of Italy that you showed before, like between Tuesday and Sunday. And have you ever traced the impact on climate of massive migrations of people?
No is a short answer to that. Not as far as I'm aware. I mean, one can look at the changes in population distributions, but I mean that's not. But the direct consequence of their effect on climate is mostly concerned, I would say, direct measurements that do with urban heat islands and the increasing locality of focal points of heat, which you get in cities. But I think otherwise, no, they're more a consequence of climate change than a cause of climate change, I'd say.
So like when people from Syria migrated to Turkey, where like 2 million people, they had no effect on climate.
I think...
So like they could stay below the 1.5...
I think, yes, I think that's certainly to first and probably second order, that's the case. Much more problematical is whether they were driven, to what extent they were driven by climatic change, and to what extent the whole unfolding of this Syrian catastrophe has been, at least in part, caused by changes in climate is more problematical. There are two schools of thought on that. There's quite a strong paper published about 4 years ago which explained just what the linkages were, and another paper about 3 months ago which disagreed with all that and said no, that wasn't the case. So we're still not quite sure. I wouldn't put it more than it's a possibility, but it doesn't require much imagination to realize that if you have, particularly in areas, so let's say like sub-Saharan Africa, large populations which are already borderline dependency on food security, where we know there's likely to be significant decrease in security of agricultural produce in the future, then that's likely to have some effect on changes in population distributions, whatever that may be and wherever they may go afterwards. I'm not saying they're going to go anywhere, but it's likely to have some significant effect. And as you saw, unfortunately, locally, the temperatures and the changes in our local environment in Northern Europe are likely to be not necessarily catastrophic for us, possibly even potentially beneficial in the very local sense. But we will be implicated in the problems elsewhere. I sincerely hope anyway that we won't be isolated from those, and the world will not be as a whole a better place for the consequences of that.
Another question online, and I'll ask the question but then also ask a broad question around it as well. So the question itself is, will improved monitoring networks in terms of emissions impact transboundary air pollution cases? I guess that's in terms of legal aspects of it to some extent. And I guess that then, more broadly, I mean, do you see Earth observation measurements, starting to be used more in terms of litigation? I mean, in the land of lawyers in the United States, forensic meteorology has been around for a very long time as being a big industry. Do you see that sort of side of things?
There are some specific cases where even almost 20 years ago was the first case I remember of a ship which was identified in the Singapore Straits, cleaning its tanks and dropping oil, and was fined about, I think, $2 million at the time, on the basis of satellite evidence of its track, where it was, and the evidence of the oil slick which it left behind. So there are some cases. There have been cases also for some construction work in northern Italy at a site near Milan, where there was an argument about some damage that was caused in a set of residential areas. And somebody had been building a car park nearby, and they argued that there's nothing to do with it. And they looked back at the historical evidence and showed that the subsidence which had occurred in these houses occurred exactly at the time when this car park was built, and so that was used. So there have been individual cases where that's been used. But coming back to the original question, so I think the groundwork has been laid and there have been other cases. In London, there's the International Institute for Space Law, I think it's called, run by Saeed Mostashar. And they've had several workshops in the last couple of years that I've worked with them, where looking at uses of evidence from space, it's called. And it was cases of litigation and legal cases which were based on evidence gathered from satellite platforms. There aren't many of them, but there are enough to establish that there are precedents. The question about transboundary pollution, really, the interesting question is to go back, if we might do something about CO2, think about what happened with acid rain and SO2 in the 1980s. I can young enough to just about remember that. And I remember at the time, Alan Appling, Robert is here from ex-Department of Environment, and he'll probably remember Alan Appling, who was responsible for it at the time. And he explained to me that everybody knew where the acid rain was coming from. Everybody knew where the SO2 was coming from. But because there's the transport models were not sufficiently precise, those polluting countries, mostly in Eastern Europe at the time, who were emitting the SO2, which was then combining with water and rain, and then dropping as acid rain in Scandinavia, they were able to say, well, the evidence is not sufficiently strong from the transport models. They aren't accurate enough to actually deliberately pin the blame on my particular emissions. As soon as the transport models were good enough, they realized they were banged to rights, and they just said, right, yes, okay, fine, it was us all the time. But they were able to argue until that point that it wasn't them, because nobody could prove it was. So it was not so much the emission measurements. Everybody knew how much they were emitting, but nobody could prove where they were going. It was the transport models, actually, which were the key point in being able to use that. And that became legally established and was used then as compensation and so on. So it's not just the observations, it's also the models which need to be built.
I wonder if you could comment on what impact you think President Trump will have on Earth observation capability And I'm thinking particularly of, who will be looking at what where.
Well, Charlie's here, can probably answer that question better. Two points. Firstly, how much effect will Trump have in terms of climate? On the whole, touch wood, not much. The US is more or less behaving as it was, and President Trump is the odd man out. He may be courting the big oil and big coal in particular, but in fact, there are 3 times as many people employed in renewable energy industry in the US as there are in coal. And on the whole, the US economic institutes and industry is wholly behind the support for things like the Paris Agreement and so on, because they realize this is actually in their best interests. I think that's an important point that we've turned. We're not doing things which are altruistic against our own interests. We now, I think the world is beginning to realize that it's doing things which are coincidentally both to its own benefit and to the benefit of everyone else. And many people in the US and industries and states, I know Charlie's just come back from California where he's highly involved with that, he could say something about it. Many states in the US are already completely contravening the federal perspective on things. So I'm pleased to say that I don't think that politically it will have as much effect. The other point is that fortunately in the last budget for NASA, the Earth observation budgets for NASA were very, very small cuts made. So the satellite observations are pretty well robust. There's one particular mission which was cancelled, or not cancelled, delayed, which is not the first time a mission has been delayed. So more worryingly a little bit is to do with the NOAA, the agency which is more responsible for climate observations. And there have been significant cuts there, particularly not so much in the satellite base, which are not so much targeted. There we tend to use weather satellites for climate observations. So the weather satellites are there for weather, so we don't build so many climate satellites via NOAA. But they've had to do some of their work a little bit lower, with a little bit less publicity than they were doing in the past. They're doing as best they can, but they will suffer by something like 25-30% cuts in their area. NASA's in Earth observation suffered only about 1%, something like that. I know, Charlie, you're more on top of it than I am.
Well, I think in a situation like this, it is fairly easy. It's easy to maintain a going concern because the politicians will defend it. And so it's for this reason, I think, that the current set of Earth satellites will continue, and that would have been a loss to the international community. The question will arise, however, when you want to try to do something new and you have to propose a new program, and people then will challenge your premise for that program on political grounds. So it may be more difficult to innovate in future because of the current political situation. On the other hand, I just would like to report that the state of California will sponsor an international global conference on climate change in September in order to prepare arguments for the coming Conference of Parties meeting that will take place in December. So there you are.
There speaks the chairman of the chairman of the California Council on Science and Technology.
Thank you very much for the talk. My question is to what extent, or you can comment your comment on how the Earth observations could help us choose the right way forward, or advise on the geoengineering methods that are being suggested to deal with the problem, or how best could this help, and what do you see the role they play in policymakers deciding on what path to follow? Thank you.
The narrow answer to that question is that at present it's not clear that satellites have very much to offer in that area, other than, I guess, looking to see what the consequences might be at some later date. But I'm pleased to say that there isn't much enthusiasm for geoengineering around the world at present, and I hope it stays that way. There are one or two very erudite individuals who have been advocating something along those lines, either by sowing iron filings in the ocean in order to create CO2 drawdown, or by seeding clouds and so on. I personally think we've done enough experimenting with the planet already, thank you. and we're probably better to try and remove some of the effects that we've already had rather than introduce new ones. So I hope that we're not, and that seems to be receding, to my perception anyway, that 10 years ago there was quite a lot of discussion about geoengineering, but I don't see so much these days.
So the question of politics came up before, and it seems to be hard to convince politicians to do something. So what can be done without them? What can be done bypassing politics?
Well, we'll find out in the US, I guess. I think Charlie's made a good point that a vast majority of industry in the US and the economic focus in the US is behaving as if President Trump didn't exist in terms of climate change. And the policy of the US as a nation, despite what this president may be saying, are continuing more or less on the same lines as they were before. So I think there are some entities which are already quite well convinced. I think we should be trying to provide the evidence for politicians worldwide and to allow them to be persuaded to make the right decisions. But we need to convince them to base their policies on evidence, as I said, not the other way around, which is unfortunately what happens occasionally.
Well, we've come to the end of our time, so thank you very much to all the people who've been watching online and sending in questions, and to everyone in the audience. I've certainly found it fascinating to hear the discussions this evening, Stephen. I mean, it strikes me that 50 years ago we were...
the world was getting very excited about the dawn of the space age and sending people, to the moon and so forth. And I almost feel that, 50 years later, we're sort of at, another dawn of a new space age. Just the amount of information that we're able to get in terms of understanding our planet and how it's changing from space is just remarkable now. And the increased capability of being able to use that and the promise of being able to use it in terms of really making more accurate and fine-grained decisions.
Very much for bringing that to us this evening. Perhaps we can all give Stephen a round of applause.
Thank you very much.